Have you ever tried to hear a single whisper in the middle of a crowded, sold-out rock concert? You know the person next to you is trying to say something vital, maybe the secret to your entire research project, but you are surrounded by 50,000 watts of heavy metal and 20,000 screaming fans. In the world of high-resolution mass spectrometry, that whisper is your biological signal, and the concert? That is the noise. Now, have you ever felt that specific, crushing weight of opening a spreadsheet with 5,000 rows? You've spent weeks in the lab and processed your data into a beautiful feature table. But the moment you open that file, you realize you have 10,000 m/z values and no earthly idea which one is your smoking gun. Most researchers fail here because they treat every data point as equal. They waste months on solvent contaminants or electronic glitches. In high-stakes consulting, we call this sifting for the value drivers. Today, we master the mathematical sifter to find the 1% of truth within the noise. Before we pick up our statistical tools, we need to understand the strategic logic of sifting. In our previous modules, we cleaned the kitchen and aligned our features. We have a clean table, but it is still just a list of names. It doesn't tell us who is important. Think of this phase as a high-stakes job interview. You have 10,000 applicants for a single position. You cannot interview all of them in depth on day one. You need a series of filters that get progressively more sophisticated. We start with univariate analysis, the individual interview, to see who stands out on their own. Then, we move to multivariate analysis, the group dynamics, to see how these molecules work together as a system. This isn't just about doing stats. It's about building a case that can stand up to a global audit. By the end of this session, you'll have the courage to say what is real, and the wisdom to ignore what is just hiss. To find the ultimate truth in your data, we utilize a 3-tiered funnel. Each level provides a deeper level of strategic insight. Level 1 is univariate analysis. We use t-tests and volcano plots to perform an individual interview on every molecule, looking for those with significant change and high biological impact. Level 2 is unsupervised learning, specifically principal component analysis, or PCA. This is the drone view. We want to see if our groups naturally cluster together, without us telling the software who is who. This is our reality check. Finally, Level 3 is supervised learning via PLS-DA. This is the strategic hammer. Here, we tell the software which samples are sick and which are healthy, and we ask it to find the specific molecules, or VIPs, that drive that difference. This framework ensures your discoveries are mathematically sound and biologically relevant. We start broad and finish with a laser-focused MVP list. The first step in our sifting process is univariate analysis. We take every single molecule on your list, all 10,000 of them, and we interview them one by one to see if they are behaving differently between your groups. We typically use a student's t-test to compare 2 groups, or an ANOVA for 3 or more. But here is the secret. A low p-value by itself is a dangerous metric. You can have a molecule with a p-value of 0.0001, but if it only changes by 1%, it isn't a biomarker. It's just a very precise instrument. In clinical relevance, 1% is noise. To find the truth, we use the volcano plot. The x-axis is the fold change, the actual increase or decrease, and the y-axis is the negative log of the p-value, how sure we are that the change wasn't random. The winners of your study are the molecules in the upper left and upper right corners. They had a massive biological impact and passed the statistical audit. Now we move to multivariate logic with PCA. Think of PCA as a drone view of a massive crowd. If you fly a drone 50 feet up, you can suddenly see patterns invisible on the ground, like fans in red shirts clustered near the stage and blue shirts near the food stalls. PCA takes your 10,000-dimensional spreadsheet and mathematically reduces it to 2 or 3 principal components that capture the most variation. We don't tell the software which sample is which. We let the data speak for itself. Here is the consultant's reality check. If your control and treated groups do not naturally separate in a PCA score plot, your biological signal might be smaller than the random noise in your system. A pro always starts here to spot outliers, those samples floating far from the rest, before they ruin the final conclusions. It is the ultimate tool for assessing analytical integrity. What if the groups almost separate in the PCA, but there's too much overlapping noise? We reach for the strategic hammer, PLS-DA. In PCA, we just observe. In PLS-DA, we intervene. We tell the software which samples are sick and which are healthy, and we ask it to find the specific molecules that predict the difference. The most powerful output is the variable importance in projection, or the VIP score. Think of the VIP score as the MVP list of your study. Any molecule with a VIP score greater than 1.0 is a significant driver of the difference. These are your candidate biomarkers. We take this list and see if they belong to the same biological neighborhood, like lipid metabolism. This is the bridge where you move from a mathematical score to a real-world discovery. You're no longer just looking at dots. You're looking at the engine of the disease. Before we celebrate, I have to give you a consultant's warning about a major trap: overfitting. If you give a powerful enough algorithm enough random numbers, it will eventually find a way to separate them. This isn't science. It's a mathematical hallucination. An overfitted model has memorized the noise of your specific samples instead of learning the true biological pattern. To avoid this, we use cross-validation. We hide some data and ask the algorithm to predict which group those samples belong to. We look at the Q-squared value, which measures predictive ability. If your R-squared is high, meaning the model fits the data, but your Q-squared is low, your biomarkers are just noise. In strategic data stewardship, we never trust a model that hasn't been tested against reality. We want a model that is robust, reproducible, and ready for the real world. As we wrap up our sifting session, look at the decision matrix. You start with the volcano plot to identify high-impact winners through individual interviews. You use PCA as your drone view. If samples don't cluster here, your biological signal may be too weak. Then, you use PLS-DA as your strategic hammer to find the VIP molecules. But remember the final gatekeeper: validation. A beautiful plot is worthless if it isn't predictive. By applying this three-tiered funnel, you ensure the molecules you present to your stakeholders are the ones that actually matter. You have moved from a data collector to a data strategist, with the power to defend your results under global scrutiny. We have completed our statistical audit. Today you learned the 3 levels of sifting that turn a chaotic spreadsheet into a map of discovery. You've mastered volcano plots for individual impact, PCA for unbiased trends, and PLS-DA for finding the VIP drivers. You now have the analytical confidence to stand behind your data. Remember, statistics isn't just about the math. It's about the courage to say what is real and the wisdom to ignore what is just noise. You are no longer looking at jumbled M/Z values. You are seeing the biosignature of your experiment. But even after this work, one major hurdle remains. Once you've found that MVP molecule with a VIP score of 2.5, you still don't know its name. You just know it weighs 342.1158 daltons. In our final unit, Module 10-6, Naming the Peak, we will finally give them a chemical identity. I'll see you at the database.